Okay, electron configurations in the periodic table. Valence electrons. What are valence electrons? Valence electrons are the electrons in the outermost principal shell, meaning they are in the highest energy level. So in the quantum hotel, these are the electrons staying on the highest floor in the hotel. These electrons are important because they are the ones that are farther out, they're on the outside, and those are the electrons that interact with the electrons of other atoms and are responsible for many of the properties of the elements. So any electrons that are not valence electrons are called core electrons. So those are the ones on the inside. The valence electrons are the ones on the outside, core electrons are the ones on the inside. So if we look at the electron configuration for silicon, 1s2, 2s2, 2p6, 3s2, 3p2. To identify the valence electrons, we're looking for the highest principal quantum number. So this is quantum number 1, 2, and 2, and 3, and 3. So 3 is the largest principal quantum number. It's the highest floor in the hotel that has electrons staying on it. So all of the electrons in the third level are considered valence electrons. So the 3s2 and the 3p2. So there's a total of 4 valence electrons here. Do you see that? In the blue here, these are core electrons. They are staying on lower floors in the hotel. What group on the periodic table is silicon in? Not period. What group? Vertical. 4A. Group 4A. Group 4A and silicon has 4 valence electrons. That's not a coincidence. Let's look at chlorine and identify valence and core electrons. So, using the periodic table, we should be able to say the last term in a chlorine's electron configuration. So it's in period 3, the third row. So it's going to end with 3, and chlorine is over in that P block, that group of 6 columns. So 3P. And how many over is chlorine? 5. So the last term is 3p5. We can read that off the periodic table. Before 3p is 3,2. 3,2. 3s, s's sometimes look like 2's. No, they don't. 2's, what is wrong with my brain? 3s2, that's what I was going to say. And before that, there's 2p6 and 2s2 and 1s2. So that's the electron configuration. Valence electrons, we're looking for the highest principal quantum number, the highest level that has electrons. What is that? 1, 2, or 3? 3. So we have electrons in the third level, right? So I'm just going to put a box around all the terms that have 3. It's 3s and 3p. There are electrons there. Now I'm going to look at the superscripts. 2 and 5, add those together, is 7. So there are 7 valence electrons for chlorine. Anything that's not a valence electron is a core electron. So these are the core electrons. So you could take 2 plus 2 plus 6 is 10. I'll call those CE for core electrons. So valence electrons and core electrons. Any questions? What group on the periodic table is chlorine in? Group 7A. So there's 2 sets of numbers up there. There's 1, 2, 3, 4, 5, all the way through 18. Those are nice, but they're not as useful as the other one that has the letters. 1A, 2A, and then it skips over the transition metals, 3A, 4A, etc., up to 8A. Those group numbers with the A's after them tell you how many valence electrons the elements in that column have. So chlorine is in group 7A. It has 7 valence electrons. So here we've got just some of the main group elements. So here's group 1A. Hydrogen has 1 electron. It has 1 valence electron. Here's lithium. It has 3 electrons, but only 1 valence electron. Sodium has 11 electrons, but 1 valence electron. All of the elements in group 1A have 1 valence electron. Let's go over here and look at group 3. All of these guys have 3 valence electrons. So that's pretty easy, right? Group 8A, here's helium. Helium is one of those baby brothers who gets away with breaking rules. It's over here in column 8A. Because it is a noble gas, it's very inert, but it doesn't have 8 valence electrons. It only has 2 electrons, so it can't have 8 valence electrons. So in some ways it belongs over here, but in other ways it belongs over there. So the reason that we see this periodicity in the properties, the reason that the group 1A elements have similar properties, they're all very reactive, is because they all have 1 valence electron. The reason that the noble gases are unreactive is that they all have 8 valence electrons, except for helium. But they have as many electrons in that highest level as are possible. You can't have more than 2 electrons in that first level. So valence electrons for main groups are the group number, except for helium. And the row number tells us the highest principal shell. So if you wanted to know, say for phosphorus, what is the shell, the principal shell that those valence electrons are in? Well, it is in the 3rd period of the periodic table. 1, 2, 3. It's in the 3rd period, and so its valence electrons are in the 3rd level. Any questions? So we can look back here at this full periodic table, and we can see, here's radium, big guy down here. He's in group 2. He's got 2 valence electrons. They're in the 7th principal energy level or principal shell. You can look at polonium, group 6. We predict 6 valence electrons. 2 plus 4 is 6, and those are in level 3. Level 6. Oh my goodness. Any questions? So what about those transition elements? Transition elements are a lot less predictable than the main group elements. Most of the transition elements are going to have 2 valence electrons. And we'll go ahead to the next periodic table. So these are the transition elements. So here's scandium. It has 1 more electron than calcium. So calcium ends with 4s2. And then this is the D block. And the D block is one level lower than the period. So it's not 4D, it's 3D. So when we look at scandium and count valence electrons, we're looking for the highest principal level in the hotel, the highest floor that has electrons staying on it. Well, there are electrons on the 4th floor. There's also an electron in this 3D room, but that's not the highest floor. That's not a valence electron. Only the electrons in that highest floor, the highest level, are valence electrons. So scandium has 2 valence electrons. Titanium has 2. Vanadium has 2. Iron has 2. Nickel has 2. Because we've got 2 electrons on that highest floor, and then these other ones are coming in, and they're taking that last room on the floor below. Okay, so they're not valence electrons. They're filling up core electrons. Does that make any sense? So, you look at the electron configuration for vanadium, which would be argon plus this part, 4s2 and 3d, 1, 2, 3. So vanadium would be argon, 4s2, 3d, 3. Bless you. So what's the highest level? 4. 3d is listed after, and it is higher in energy, but it's not the highest principal quantum number. So only the electrons in the fourth one are valence electrons. So these are the valence electrons right here. 2 valence electrons. How many core electrons does vanadium have? Well, it's got these 3, and however many electrons argon has. An easier way to do it is, well, the rest of the electrons are core. How many electrons total does vanadium have? 23. So it has 23 electrons total. And if 2 of those are valence electrons, then there must be 21 core electrons. Argon has 18. Those are valence electrons, 19, 20, 21. 21 core electrons, 2 valence electrons. So most of the transition metals have 2 valence electrons. Any questions yet? Yeah. NB?
Under the vanadium.
Oh, it is. I have been looking at this periodic table for years, and I haven't seen that. Thank you. I usually see stuff like that. And look at that. 45S1D4. That's messed up. So that should be 5S1 4D4. Good one. Anything else? I found some pretty crazy typos in this book. Oops. So there's 2 exceptions in that first series of transition elements. Let's look at those. We're going along 2 valence electrons, 2 valence electrons, 2, 1 valence electron. What the heck? 2, 2, 2, 2, 1, and 2. So chromium and copper are exceptions. And the reason, I'm not going to spend too much time on this. For chromium, doing it this way, the 4s is exactly half full and the 3d is exactly half full. So in the hotel, that's like there's a special if you've got all the beds with one person. So by moving a person from the 3D, the 4s up to the 3D, you can satisfy that, and that's more stable. And here with copper, this one's half full and that one's completely full, and that's also an energy bonus and more stable. So I'm not going to expect you in 3A to remember those, but I just want to tell you they are there, and there's more as you go larger in the elements. There are reasons for that. Okay, it's not those aren't typos. That niobium thing was a typo. So if we want to write the electron configuration for phosphorus, we can pick this off the periodic table. We find phosphorus over here. This is the first period, so we go 1. This is the S group, 1s, and there's 2 blocks. That's 1s2. This is 2s2. This is up here 2p, 1, 2, 3, 4, 5, 6. This is 3s2, and we skip across there, and this is the 3p, 1, 2, 3. So the electron configuration for phosphorus is 1s2, 2s2, 2p6, 3s2, 3p6, 3p3. How many valence electrons does phosphorus have? 5. So there's, as with many things in life, there's different levels of understanding things, right? There's like thoroughly understanding it, and it'd be great if we could all do that with everything, but it's just not possible. And then there's understanding it enough to get done what you need to get done, right? So it would be great if you all really understand what all this nonsense is and how you see that there's 5 valence electrons. The most important thing, though, is that you be able to look at the periodic table, find phosphorus in group 5A, and tell me it has 5 valence electrons. That part is easy. Understanding this is, yeah, that's hard, especially if you've never heard about it before. But very important, phosphorus has 5 valence electrons. This element over here, how many valence electrons does it have? 7. And how about this one over here? 1. Group number of the main group elements tells us the number of valence electrons. That is a summary of what we've talked about. Let's do another example, electron configuration for tin. Well, first thing is we have to figure out which one is tin. Anybody know the symbol for tin? SN. And then we have to find it. Where'd you go? There you are. So there's tin. So if we're going to go through and write the full electron configuration, we're going to start here at the top. This is 1, and the blue ones are the S. So we've got 1s, 2. And then we come here, and what does this represent? 2s, 2. And then over here, 2p6. Actually, I'm going to draw some lines here. So we did those. That was 1s2, 2s2, 2p6. What's next? 3s2. And then we go over here, and this part is 3p6. And we come over here, 4s2. And then these guys in the middle, what are those? Those are Ds. Are they 4D? Well, they're 3D. 3D, and if you forget how many electrons can fit in there, you can count the columns. That's 3D10. And then over here, P block again. What's the number for that P block? 4. The S and P blocks use the period number. The D blocks use the period number -1. So this is 4p, and that one's full, 6. And then over here, what's this part? 5s2. And then this part, 4d, 10. And then 5p2. So if you practice a little bit, it's all of that is hiding in the periodic table. Okay? But most important, how many valence electrons does tin have? 4. It's in group 4. Okay?